We will take a look at guidelines for factoring a polynomial. First, always look for a common factor between the terms other than 1. If there is one, factor out the largest common factor. Be sure to include this factor in your final answer. And you can see here we have the binomial with the greatest common factor of 5. Factoring it out then has the following: 5 times the quantity of the remaining binomial, t to the 4th minus 16. We would then continue on with factoring the remainder. Next step is to look at the number of terms. If there are 2 terms, we want to check to see if we have a difference of squares, then factor accordingly. Difference of squares, a squared minus b squared, factors into conjugates with the first and second terms being the same, one a sum and one a difference. In this example, we start with factoring out the largest common factor, which is 2x. Then, since the remaining polynomial has 2 terms, we determine whether it is a difference of squares. If it meets the criteria, we would continue with factoring it as well. And since we have x squared being a perfect square and 9 being a perfect square of 3 squared, we would then continue with factoring and breaking it down into the difference of squares. If there are 3 terms in the polynomial, the first thing to consider is whether it is a perfect square trinomial. Checking for a perfect square trinomial can be done rather quickly and should follow the pattern for one. To do this, check both the leading terms and the constant term of the trinomial to see if they are squares. If they are not both squares and there is no common factor, the trinomial cannot be a perfect square trinomial. In this example, we first factor out the largest common factor, which is 2. Looking at the remaining polynomial, since it has 3 terms, we will first check to see if it is a perfect square trinomial by determining whether it follows the pattern for one using the 3 criteria. Is the first term a perfect square? Is the last term a perfect square, 25 being 5 squared, and then multiplying the square root of each, x times 5 and doubling it, does fit the 3 criteria that we do in fact have a perfect square trinomial that we would then continue with the factoring. If the 3-term polynomial does not meet the criteria for a perfect square trinomial, as we just saw in the last screen, then we try using the FOIL guess and check method for factoring. In this polynomial here, we start by factoring out the largest common factor, which we see is 2. There are 3 terms remaining, but they're not a perfect square trinomial because negative 10 is not a perfect square. This means we move on to factoring it into binomials. Since the leading coefficient of the first term is 1, the first term in each binomial will be x. The constant term is negative 10, so the last term in each binomial must be one of the following factor pairs if this trinomial is factorable: 2 and 5 or 1 and 10, with one being a positive and the other factor being negative. After checking the combinations, the factorization of this polynomial is 2, that greatest common factor, times these 2 binomials that result in that trinomial that we have highlighted here. Continuing on, if we find that we have a polynomial with 4 terms, we will try factoring by grouping. In this example, we will try factoring the first 2 terms and the last 2 terms. The first 2 terms have a common factor of 2x, and we can even go as high as 2x squared. And the last 2 terms do not have a common factor other than 1. After factoring the 2 pairs, we have a common factor of x plus 5 in each, which we can factor out, leaving 2x squared plus 1 times the quantity x plus 1. The last note on factoring is to be sure that the polynomial has been factored completely. Can we break this down? We have 2 terms. Is it a difference of squares? There's no difference. 2 is not a squared. We have factored it completely. And realize that sometimes polynomials are not factorable, so are listed as prime. So let's take a look and follow the general steps just covered for factoring a polynomial in these examples. First order of business is to look for a common factor. Here, the largest common factor is 10. Factoring out the 10 results in 10 times the remaining factors of x squared minus 16. Since the remaining polynomial has 2 terms, we'll now check to see if it is a difference of squares. First term is a perfect square. The second term, 64, is 8 squared, so it follows the pattern of a difference of squares, which means we can factor it into conjugate pairs of square root of the first term, square root of the second term, with one binomial a sum and the other a difference. Check, of course, the multiplication to verify that we have, in fact, factored it correctly. In this example, after checking for a greatest common factor, which there isn't one other than 1, since it's 4 terms, we will factor by grouping. For just ease, we'll factor the first 2 terms and the last 2 terms. The first 2 terms have a common factor of x squared, and the second 2 terms have a common factor of 4, but since both of the first 2 terms are positive, factoring out a negative 4 anticipates the problem of the signs not agreeing. So factoring out the largest common factor in the first 2 terms results in x squared times the remaining binomial of x plus 3. Factoring out or dividing the last 2 terms by negative 4 leaves x plus 3, and we have that common binomial between the 2 terms that we then can factor out, leaving the x squared once x plus 3 is factored from the first, and a minus 4 when the x plus 3 is factored out of the second. We need to always, before we're done, ask the question whether this is factored completely. Whenever you have a power higher than 1 on a variable, you should be suspicious that it may not be factored completely, and that is the case here. We have a 2-term polynomial, and it does meet the criteria for a difference of squares. Square root of x squared is x, square root of 4 is 2, and we have our difference. Factoring then with the square root of the first and the second, one being a difference and one being a sum, we have factored this 4-term polynomial into the following here that we can check by multiplying to verify whether it's correct. In this last example, first thing is to look for a greatest common factor between all 3 terms, which is 3x. Writing those factors of 3x for each term and then factoring out or dividing the 3x from each leaves the trinomial here of 3x squared plus 4x minus 15. We have a 3-term polynomial. It is not a perfect square since 3 nor 15 are perfect squares, which leads us to using the FOIL method of guess and check. 3x squared comes from 3x and x. Factors of negative 15, we have a couple choices. Choices being the following. One of the factors needs to be negative and one positive. So we have 3 and negative 15, and then switching those signs for those possibilities here. And checking each one of these to look for that middle term of 4 using the FOIL method. It hasn't occurred yet. Here they add up to be a negative 4x. We're close. And checking here with this combination, we do in fact have the positive 4x, which gives us those factors. If these had not worked, we would have used 15 and 1, with 1 being positive and 1 being negative as well.